Now let's see the components of three-phase induction motor. As already said, the three-phase induction motor will be having two components. One is the stator, which is stationary part, and the other one is the rotor, which we call it as a rotationary part. See, in this picture, you can see that this particular part is called as a stator, and this is your rotor. This will be inside this structure, and it will be rotating in nature. Okay, this one is called as a shaft, which will be available for us outside, so that we can connect it to the requirement based upon the requirements. Okay, the construction is very simple and it is very robust. That's why we are using induction motors very widely nowadays. Okay, so in the stator, predominantly there will be three parts, which you call this one as a frame, which is your outer part, which basically provides you mechanical support, and this is your core, where you will be housing your poles, and these poles are basically electromagnets. So that's why you will be having copper wire wound upon these poles such that they will behave like a magnet, right? So internally you will be having windings. Okay, so this is your stator frame, and this is your stator core, and this is your stator winding. Okay, so these three are the important parts of your stator. The next one is your rotor. So let me start with the stator frame. As already said, stator is a stationary part, and the stator consists of three main parts. The first one is the stator frame, which is your outer part of the motor. Its function is to provide support to the stator core and stator winding, and it provides mechanical strength to the inner parts of the motor. It houses this internal core and also the windings. It will be having fins on the outer surface. See, I'll show you. These are the fins. We call these things as fins. See, these are used for heat dissipation. Okay, they will provide air circulation, good air circulation. Okay, so that your motor gets cooled. These are called as fins. Okay, and this entire frame, for if it is a small machine, if you are not looking for a larger efficiency, you will be casting for small machines, and if it is a very big machine, you will be going with fabrication. You will be taking too many pieces and then you will fabricate the entire frame. Normally it is made up of iron, cast iron, and if you want more efficiency, you can go with steel, fabricated steel, or if you want a lightweight one, you can go with aluminum. Okay, and next comes a stator core, which basically is a part of your magnetic field development. The core carries the AC magnetic flux. So poles are a part of this core, so over which your windings will be there. Whenever current flows through these windings, you will be getting a magnetic field, and this magnetic field is essentially carried by this core. So in this process, it will develop magnetic losses, which we call it as hysteresis and eddy current losses. And to minimize these losses, your entire core will be laminated. Instead of using one big piece of core, it will be laminated, and between these laminations you will be providing an insulation. Okay, very thin laminations will be there. See, thickness will be something like this, and these laminations will be separated because the heat or whatever the magnetic loss, it must not be extending to other material. That's why we are going for the lamination. So the separation will be dealt with the varnish. It will act as an insulating material. Okay, so all these laminated things, they will be stamped together in the form of a core, and it is fixed inside your stator frame. Okay, and this inner part, it will be having, if you see at the inner part, it will be having several slots through which your windings will be placed. Now stator winding, this is the most important one. This is responsible for carrying of current, setting of magnetic field, which is then carried by your core. So windings are placed inside the stator slots, which are available in the core. Normally you will be using a three-phase winding. It will be given a three-phase supply, as already I have shown you, 120 degrees apart. How many poles you are using, it depends upon your internal connection of the stator winding. If you use more number of poles, you will be getting different speed. Say, as already I said, if you use higher number of poles, the speed will be low. If you use less number of poles, the speed will be high. Okay, so this is what I have written. If the number of poles is greater, speed will be less. If the number of poles is lower, then you will be getting a high speed. Normally the number of poles will be an even number. It will be in pair. Okay. And the next one is your rotor, which I have shown you as the internal part. In the rotor, you will be having conductors. So rotor is basically, it will be having slots, and in the slots you will be having conductors, which is nothing but your copper wire. So you will be wounding copper wire in the slots. And the ends of the copper wire, as already I told you, unless you don't short circuit the conductors, you won't get the machine to rotate. So how you short them, whether you short internally, if you purchase the machine, if it is already internally shorted, or you are having the wires externally and you need to short them. If you want to short them, you can directly short them, or you can use some external resistance if you want to vary the speed. So that option is given to you. Or otherwise, internally it will be defaultly short circuit. So based upon that, your rotors are divided into two types. One is a squirrel cage induction motor. The other one is a phase wound induction motor. We call it as a slip ring induction motor. Okay. Construction of stator is same in both the motors. Only the rotor construction will be different. See, the first one, squirrel cage induction motor. So in a squirrel cage induction motor, it is just like, resembles like a squirrel. Okay. So it is most widely used one. So its construction will be very simple, and it is a very rugged machine. It can withstand any type of temperatures or load conditions, etc. Okay. So here what happens is the rotor internally, it will be of a cylindrical laminated core, and it will be slots on it, and in these slots wires will be kept. So instead of using windings, they will be directly using rotor bars directly, which will act as a thick conductors. And these rotor bars, they will be made up of aluminum or brass or copper. And these bars, they will be permanently short circuited defaultly with the help of your end rings. So all these bars, they will be brought to the end, and there will be end rings will be there. So already defaultly short circuited, so that you cannot add any external resistance, or you cannot short it again. So it is not possible to add any external resistance. By manufacturing itself, it will be internally short circuited. Okay. So that's why you may not use any external materials for shorting, just like your brushes, slip rings, external resistances, etc. So that's why this construction is very simple, very robust, and very economical also. So, and it is very safe also. And the other one is a slip ring induction motor, where you will be having same laminated core. So slots will be there. Instead of rotor bars, you will be having windings, and these windings will be brought out. So the rotor winding is wound in such a way that the number of poles on the rotor winding is the same as the number of poles of the stator winding. And this rotor winding, the winding which you are using, it will be connected as a star or delta. But all these end terminals, they will be brought out, and they will be connected to the slip rings. Since it is connected to the slip rings, it is called as a slip ring induction motor. In the earlier case, there are no slip rings. So directly it is being short circuited to the end rings. You don't need to do anything. But here, slip rings will be provided for you. See, this is the picture of a squirrel cage induction motor. See here. This is a copper bars. Directly they are being shorted here. These are your end rings. But this is a wound rotor where all these connectors, they will be brought out to your end slip rings. Okay. So this is the difference between a squirrel cage motor and a wound rotor. Stator point of view, both are same. Only the rotor point of view, in squirrel cage rotor, already conductors are internally short circuited and they are connected to your end rings. Whereas in wound rotor, they will be connected to the slip rings, and you need to short circuit them externally, or you can use a resistance if you want to add while shorting them. Okay. So the applications of point of view, squirrel cage induction motor, they are extensively used in submersible pumps or overhead pumps, in pressing machines, lathe machine, grinding machine, conveyors, etc. All very rugged type of applications. So you will be using them. Squirrel cage induction motor, or a slip ring induction motor, where you do want to change your speeds all the time. Just like your mills, lifts, cranes, where you need to adjust the speeds some or other how. In these cases, you will be using slip ring induction motor. Okay, so for heavy lifting, lifts, cranes, hoists, these do require heavy lifting, right? So for that things, you will be using slip ring induction motor. You can add additional resistance so that you can increase the torque. Okay, that's way out of your syllabus, but try to remember a few applications of both squirrel cage and slip ring induction motor. Now we will move on to simple problems on three-phase induction motors. But before going to that, let me take a closure of this one. and I will explain to you the problems in the next video lecture. A small 3 or 4 minutes. So let it make a separate one. I'm closing